All right, we want to find the limit as x approaches 1 of g of x. So we need to consider the limits from the left and from the right. Let's take a look from the left first. Coming in from the left means we're choosing x values really close to the number 1 and substituting them into the g function and seeing what the pattern of heights are, intended height. All right, so let's say that I substitute in negative 0.5 into the g function. That is a number really close to 1 from the left. We get an answer out of about 0.5. Okay, then I substitute in 0, which is a number even closer to 1, and I get out an answer of 1. Then I substitute in, let's say, 0.9. 0.9 is really, really close to 1 from the left side, and I get out a height of 1.9. So as we continue to choose x values really, really close to 1 and substitute them into the g function, the height is getting closer and closer to 2. It doesn't matter that the actual height of the function is only 1. If I plug in 1 into the g function, I get out 1. I'm not substituting 1, I'm only picking numbers closer and closer to 1 from the left side. And the pattern of heights, the pattern of answers, is heading to 2. All right, now let's come in from the right side. If I were to substitute an x value of, say, 2, which is kind of close to 1 from the right, I would get out a height of maybe 3. If I substitute in, say, 1.5, I would get out a height of maybe 2.5. And then if I substitute a number even closer to 1 from the right, let's say 1.1, I would get out a height of about 2.1. So as we get closer and closer from the right-hand side, the heights are heading to 2. And since the intended height from the left and the right are both 2, well, then the limit as x approaches 1 of g of x is equal to 2. We want to find the limit as x approaches 1 of h of x. Considering the limits from the left and the right, I start substituting in numbers close to 1 from the left. So say I plug in negative 1 and I get an answer of 0. I plug in negative 0.5, I get an answer of 0.5. I plug in, let's say, maybe 0.2, and I get out maybe 1.2. And then I substitute 0.9, which is really, really close to 1 from the left, and I get out a height of 1.9. And so the heights, as I plug in numbers close to 1 from the left, is heading to a height of 2. Similarly, finding the limit as x approaches 1 from the right, I substitute in a number close to 1 on the right, say maybe 2, and I get out about 3. If I substitute in, say, maybe 1.5, maybe I get a height of 2.5. Keep going, I get even closer. I substitute in maybe 1.2, and I get out 2.2 as the height. So as I pick numbers closer and closer to 1 from the right, the heights are heading to 2. And since the limit from the left and the limit from the right, the intended height from the left and the intended height from the right are the same answer, then the limit as x approaches 1 of h of x is equal to 2. You might be thinking that all limits have answers after doing those ones. So let's take a look at one more here. I have this function m of x, and I want to find the limit as x approaches 1. To find the limit as x approaches 1, I need to consider the limits from the left and the right. So let's look at from the left first. We're picking numbers really, really close to 1, but we're choosing those x values from the left. So if I select an x value close to 1 from the left, maybe I plug in 0. If I plug in 0, I'd get out 1. If I pick another number close to 1 from the left, maybe I plug in 0.5. 0.5 substituted into m of x gives me about 1.5. Then I plug in maybe 0.9 into the m function, and I get out about 1.9. And so as I'm selecting x values and substituting them into m of x, and I'm picking them closer and closer to 1 from the left, the heights are heading to a height of 2. All right, now let's look at the limit as we get close to 1 from the right of m of x. If I substitute in 2, which is a number fairly close to the number 1, but coming in from the right, I'd get a height of maybe 4. If I substitute in 1.5, another number even closer to 1 on the right side of 1, maybe I get a height of about 3.5. As I substitute in, say, 1.1, which is really close to 1 from the right side, I get out a height of just a little bit more than 3. So as I get closer and closer to x equals 1 coming in from the right, the heights are heading to 3. Here we have an example of where the intended height from the left is not the same as the intended height from the right. So that means the limit as x approaches 1 of m of x does not exist. Okay, I know this video is getting long, but I feel like you still need more examples. And let's do one with an asymptote here. So let's say I want to find the limit as x approaches 4 from the right-hand side. So right there, that is the number 4. And if I'm coming in from the right-hand side, the answers to these are always heights. So think, what's the height? What's the height? What's the height? What's the height? And the height is heading to negative infinity. All right, then let's consider the limit as x approaches 4 from the left-hand side. So here's 4. If I'm coming into 4 from the left, and I continue coming in from the left, think, what's the height? What's the height? What's the height? The height is heading to positive infinity. Our sloth definition is the limit from the left has to equal the limit from the right, and negative infinity is not the same as positive infinity, so the limit as x approaches 4 does not exist. Notice this example is really similar to the last one. We are going to find the limit as x approaches 4 again. When we look at this coming in from the right, so 4 is right there, choosing x values closer and closer to 4, thinking about what is the height, the answers. Think height. The height, it's heading to positive infinity. If I come in from 4 from the left-hand side, the height, we are also heading to positive infinity. Now, this is where the sloth definition, it fails us a little bit because it's kind of lazy, and so there's a tiny mistake that can happen here. The limit from the left and the limit from the right, they are the same number. No, infinity is not a number. It's not a value. It's a concept. Saying that g of x, the limit as x approaches 4 of g of x equals infinity, in some ways, like I understand what you're saying, but rather than infinity, the preference is to say does not exist because it's not an actual value. All right, so that subtlety on the sloth definition, if the left and the right are both infinity, or even if they were both negative infinity, we're going to say does not exist because that's not a number. The sloth is going to help us answer some questions really quickly if we don't have to justify ourselves. So if you see a hole in the graph, the limit is still going to exist. And we just look at it from the left and the right. And if the curve is smooth, well, then a smooth curve, the limit's going to exist. But if you're looking at the graph and at the x value you want to find the limit, you see a break or you see an asymptote. You don't need to give those much thought. You can just say, oh, they don't exist. Now, this is not a formal definition, and we will do the formal definition next. Because really what this amounts to is If you go, oh, the limit does not exist at that number because there's a break or because there's an asymptote. Well, that's the equivalent of saying because it looks like it. And we have some formal notation that we will get to. But on tonight's assignment, there'll be a couple places where you don't have to have any reasons on any of the problems. But for the ones where the limit doesn't exist, you're going to give the sloth reason. And so the sloth reason, if the limit does not exist, might just be because there's a break in the function at that x value, or because there's an asymptote at that value.